In this video, I'm going to do a complex influence line example to show how to find the influence lines for shear and moment in a beam at a given point. I'm going to use the conventional method to draw the influence lines in the first video, and then in a companion video I'm going to use the Mueller-Breslau principle to determine the same influence lines using the qualitative influence line method. And so here we have our starting beam, which is problem 8.22 in the text. The beam has the dimensions shown, and we're asked to find the influence lines for the shear and moment in the beam at point E. So how does a load, as a unit load as it moves between A and G, affect the shear and affect the moment at point E? So in order to find the shear and moment influence lines using the conventional method, we first need to find the reaction influence lines. So we first find the influence lines for each reaction, the reactions at B, D, and G, and then we combine those influence line results in order to find the shear and the moment. At least this is generally the simplest way to do it. So first let's find influence diagram for BY. Okay, so I'm going to take a free body diagram of member AC. Okay, so it looks like this. We have A, BY, and CY and CX at the hinge. So this is a hinge. And then we have our moving load, which is a unit load of 1.0, and we'll say that X is measured from point A, B, and C. So for this part of the beam, which is between X equals 0 and X equals 6 meters, we can use the sum of moments about C to find the reaction at BY. And this is what we get for that reaction. So I've just assumed that the point load is within this beam. Okay, so the point load is at a position x less than 6, so therefore it's included in the free body diagram. I do my sum of moments. 1.0 is the unit load. 6 minus x is the distance between C and the unit load. So C is 6 from the left. X is the unit load is x from the left, so it's 6 minus x between them, and then minus by times 4, which is the distance between by and cy, and we get 1.5 minus x over 4. Now what happens once this unit load goes past C and ends up on the other side of the beam, on the other side of the hinge? Well, then we have a similar free body diagram. Okay, so we still have cy, we still have by, unknown, and cx, but we don't have our unit load now. So the unit load is out here. So we don't see it on this free body diagram. So then for conditions where x, the location of the unit load, is greater than 6 meters, which is the location of C, then we do our sum of moments again, and we find that by now equals 0. So now we can draw our influence line for this situation. Let's just draw a straight line like this. We've got A, B, C, D, E, G, for example. Okay, C is the 6 meter point. So at x equals 0, this is ID of by, kilonewtons per kilonewton. At x equals 0, we're in this situation, so x equals 0 here, that means by is positive 1.5. And then at x equals 6, we go 6 over 4 here, which is 1.5, so 1.5 minus 1.5 is 0. And then we can draw a straight line between these two. Okay, and then we can see at B, so B is at x equals 2 meters. This is 2 meters from the left. So if we put 2 in here, that's 2 over 4. So we have 1.5 minus 0.5, and at B it's 1.0. So this clearly makes sense, because when that unit load is directly above By, then all of the unit load force goes directly into the reaction and doesn't end up going anywhere else. So we have the force in the reaction, which is what our influence diagram is showing. The force in the reaction at B is going to be 1 when the unit load is directly above it. When the unit load is out here at point A, then the load in By is a little bit higher, 1.5. Okay, so let's move on to the next reaction, which is finding dy. So dy is the vertical reaction at D. So I'm going to draw a new free body diagram, and I'll draw it for the whole system this time, since now we have one known. So we have A, here's By, and C is a hinge. Then we have dy here. Then we have E at some location, and we have gy and gx. Okay, A, B, C, D, E, G. So now we know that By, when x is less than 6, then By is equal to 6 minus x over 4 when x is less than or equal to 6. Okay, so now we can use this situation. Okay, or By equals 0 when x is greater than or equal to 6. Okay, so we can use a sum of moments about point G in order to find the reaction at point D. So we sum mf equals 0. So here's a general expression for that equilibrium. So again, we're assuming that we have some point load at a location x away from A. So this is generally just in terms of By and dy. And now we have to look at two cases for this. So again, the distance between the unit load and dy is this 12 minus x, and the rest is self-explanatory. So we have to look at two different cases, because we have two different cases for By. The first is when x is less than 6, and By is equal to 1.5 minus x over 4. So if we do that equilibrium, then we end up with dy is equal to 0.375x minus 0.75. And then we also have to look at the case for x is greater than or equal to 6, in which case By equals 0. And for that situation, we get dy is equal to 3 minus x over 4. So in using this information, we can go straight ahead and draw our influence diagram for dy. That's again kilonewtons per kilonewton of unit load. So we have A, B, C, D, E, G. Okay, so we know that at x equals 0, we're in this arrangement. So if x equals 0, then dy is negative 0.75. Then we know at 6, so we're just looking at the boundaries of this location here, because we know that our influence diagram lines are going to be straight. So at 6, we get 0.375 times 6 minus 0.75, and that equals to 1.5. So we see that our influence diagram looks like this, 1.5 at C, positive. And then now at 6, if we look at the other side of C, so when x is greater than or equal to 6, if x equals 6, right, we get 3 minus 6 over 4, which is also 1.5. So we're in the same location where we start here. And then at the right location, which is x equals 12, okay, at G, we have 12 over 4, which is 3, so with 3 minus 3 is equal to 0. So then our influence diagram looks like this. And this is 0 at G. And then if we want to find out what the situation is at D, which is what we're looking at here, we have x equal to, this is 6 plus 2, which is 8. So we put 8 in here. We get 8 over 4 is 2. 3 minus 2 is 1. So we have 1.0 here. And that makes sense. So this means that when the unit load is directly above point D, then the reaction at point D is equal to 1.0. So all of the load goes directly into the reaction. Likewise, we can see here that if the point load is over B, where there is a reaction, there's a roller there, then all of the load from that unit load goes directly into the reaction at point B, which means none of it can go into the reaction at point D. So the reaction at point D is then 0. And we have the same situation at G, because we have another pin reaction here. So if the unit load is directly above the pin, all of that load goes into the pin, and none of it goes into dy. So the influence on dy is 0. So 0 at other reactions. And you'll find that this is generally the case. Okay. And we didn't calculate this one, but we could have. So if we put 2x equals 2, which is the location of B, then we get 2 times 375, which is 0.75 minus 0.75 equals 0. Okay, and then we're going to use the same situation again to find gy, except now, since we have dy and we have by, we can find gy using just a sum of the forces in the y direction. So we don't have to draw a new free body diagram and do a sum of the moments. So we can just do sum fy in the positive direction equals 0. And then we have negative 1.0, which is our unit load, plus by plus dy plus gy equals to 0. So we get, this is our unit load. We can't forget that because it acts upon the structure. And I think that that's shown in the free body diagram. Yeah, there it is. Negative 1.0, by, dy, gy. And again, we have to split this situation up into the two cases. So for 0 less than or equal to x less than or equal to 6, by, as you'll recall, is equal to 1.5 minus x over 4, and gy is equal to 0.375 x minus 0.75. So if I do that equilibrium, we find that gy is equal to 0.25 minus 0.125x. And we do the same thing for x is greater than or equal to 6. And we recall that by is 0 for that point, and dy is equal to 3 minus x over 4. Oh, and I'm sorry, up here, this should be dy, not gy. We're trying to solve for gy. So this is dy, which is what we solved in the previous step. So if I solve that, then I get gy is equal to 0.25x minus 2. So I can go ahead and draw my influence diagram for gy. This is kilonewtons per kilonewton. Okay, A, B, C, D, E, G. Okay, so we have at 0, we sub 0 into the first equation here, so we get plus 0.25, 0.25. Then at 6, we sub 6 in here, and we're going to get that at C, which is at 6, we have 0.5. So it's going to look like this. This is negative 0.5. And then now we have to switch to the other part because we have x greater than or equal to 6. So at x equals 6 again, we're going to get 3 minus, 1.5 minus 2. So that's going to equal negative 0.5. So we start at the same point here. Then at 12, we're going to get 0.25 times 12 minus 2. So that's going to be 3 minus 2. And that is going to be equal to positive 1.0. and again at D it's 0 and at B it's 0, because when the unit load is above point B, all of the load is going into the reaction at B and none of it can go into GY. And then again at G, as we expect, when the unit load is above G, then all of the load goes into GY, so the influence on GY is 1.0. So again we can see 0 at other reactions. Another thing that we can observe about this is that here we saw that our total load at G is going to be equal to 1.0 minus BY minus DY. So we could actually just combine the influence diagrams themselves. So 1.0 minus BY minus DY. So we can do 1.0 minus 1.5. So that's negative 0.5 minus negative 0.75 gives us positive 2.5. So the influence diagrams can also be combined in this way. So now that we've found the influence diagrams for all of the reactions, we can finally go ahead and find the influence diagrams for the shear and the moment at a point. So for shear and moment at point E, which is what the question asks us to find. Now when we're looking for the shear influence diagram in particular, we have to be careful of where we place our unit load, because we usually have a big step in the shear influence diagram at the point of application of the load. So for example, so we have two cases that we have to consider. One where the unit load itself is just to the left of point E, and one where the unit load itself is just to the right of point E. So let's look at these two cases. So case 1. Okay, we have x is less than 10. So here's our little piece of beam. This is between E and G. So this is just the end, this little bit here. So if we go all the way up to the top, then we're looking at just this cut. So as the unit load moves across this beam, at one point it's creating a negative shear at E. Okay, so it's pushing down on the left of point E, which creates a negative shear, and then at some point it switches just to the right of point E, and then it's going down to the right, down on the right side, which is a positive shear. So basically our shear switches signs, and it also switches magnitudes as it passes point E. As the unit load passes point E, the shear at E switches sign. Okay, so we have to take into account both of those cases. So we have one where x, which is the location of the point load, is less than 10, which means that it's left of point E, which means that it's not included on a free body diagram of EG. So we just have VE here and ME. These are our load, our shear and moment at the cut, and then the only other load here we have is GY. And again, our unit load doesn't come into play because right now we're assuming it's to the left of point E. And these two, the moment and the shear, are drawn in the positive sense according to our directional convention. So shear up on the left is positive, and moment that creates a downward bending, okay, so in this case it's a clockwise moment on the left, is a positive moment. And then case 2 is when the unit load is to the right of E, so that's when x is greater than or equal to 10, and then we have a situation that looks like this. So we still have our E and G, we still have our reaction here, and we still have our shear at the cut and our moment at the cut drawn in the positive direction, but now we also have a point load, and this is at some point x, right, which is measured all the way from point A. So we have to consider both of these. So case 1. X is less than 10. Okay, so within x is less than 10, we have to remember that we have two different situations for gy. Okay, so we're going to solve for VE and ME, but gy changes depending on the value of x. As you recall, if x is less than 6, we have one gy, and if x is greater than 6, we have another. So we actually have two subcases within case 1 for finding the shear. So for 0 less than equal to x less than equal to 6, okay, we recall gy is equal to 0.25 minus 0.125x. So then we can use equilibrium, so I'm going to use sum of forces in the y direction equals 0 to find the shear. And we find that the shear equals negative 0.25 plus 0.125x, which is basically negative gy. And then I'm going to use sum of moments about E to find the moment at E. So it's basically going to depend again on gy. And so I find that ME is 0.5 minus 0.25x, which is equal basically to negative, this is positive 2 gy. Right, and this equals negative gy. Okay, and then I have to do the same thing for x between 6 and 10. So case 1 is less than 10. So for x greater than 6, we get a different value of gy, which is equal to 0.25 minus x minus 2. And so I do the same thing and find my VE and my gy. And I get VE again equals negative gy, which is different because gy is different, and ME is again equal to 2 gy, but again gy is different. So then I can do case 2, which is where the unit load is to the right of point E, and now gy is the same as it was for x is greater than 6, which is 2.5x minus 2. So now we have this situation where we have, again, our shear. We have our moment. These are both in the positive direction. Nothing has changed so far, except now that we have our point load, and the distance between here and here is x minus 10, because this is point E and this is point G, and point E is located at 10 meters from A. So I'm going to do sum of Fy and sum of moments about E to find the shear and the moment again. And I get VE is 3.0 minus 0.25x, and ME is equal to 6 minus 0.5x. So now I know my shear and my moment at all points x, so I can draw my influence diagrams. So this is for VE, this is kilonewtons per kilonewton. Okay, so it's A, B, C, D, E, G. And I'll just duplicate that for ME. And so let's start with VE. So VE, we go to the very left, which is x equals 0. So between x equals 0 and x equals 6, VE is 0.25 minus 0.125x. So if x equals 0, this is negative 0.25. So this comes down like this, negative 0.25. Then we can look at x equals 6, which is the other boundary for the first part of case 1. So at x equals 6, we sub in 6 here, and we're going to get plus 0.5. This is 0.5. And then our next big location is at 10. So actually, let's look at 6 again on the other side of C. So if we put 6 in here again, we get 0.25 times 6 is negative 1.5 plus 2, right? It's going to be plus 0.5. So at C, both sides of C are plus 0.5. Okay, then we go to 10. So if we go x is equal to 10, then we sub in here. So we get negative 2.5 plus 2 is negative 0.5, and that's at E. So that's down here. So I draw a straight line between here and negative 0.5. And now here's where our left of E and right of E come into play. So for case 1 at 10, we got VE is equal to negative 0.5. Now for case 2 at 10, so at the same location, we sub in 10 for VE, and now we're going to get plus 0.5. So it switches between negative 0.5 and plus 0.5 at E. So we have a vertical line in our influence diagram like this. And then at x equals 12, which is location G, I sub in 12 here, we get 3 minus 3, and that equals to 0. So this is 0. And so that's the full influence diagram for the shear. And notice again that whenever the unit load, if the unit load is above B, which is a point of support, so there's a roller here, all of that load goes directly into the support, which means that it doesn't cause any shear at location E. So the value here is 0. Same at point D. So if we want to look at the moment, we do exactly the same thing, except now we're looking at the moments instead of the shear. So at 0, the moment is going to be equal to positive 0.5. I'll put positive 0.5 here. And then at 6, we sub in for 6 here, and we're going to get negative 1.0. So I'm going to draw down like this. This is negative 1.0, and that's at 6, which is point C. Then at 10, so that's 6 on the x less than 6. On x greater than 6, if I sub 6 in here again, I'm still going to get negative 1. So the moment is continuous. Then at 10, I sub in, I get 5 minus 4, which is equal to positive 1. So that's positive 1 at E, which is 10. Okay, let's move this out of the way. Negative 0.5, this is positive 1.0. And then with the moment, there's no jump. So once the unit load moves past E, it stays at 1. So if I were to sub, so that was for x less than 10, and I subbed in 10. Now for x greater than 10, if I sub 10 into the moment here, I still get 6 minus 5, which is still equal to 1. And if I put 12, okay, which is our point G, then I get 0. So it looks like this. And so that's our full influence line for the moment. So shear and the moment. And again for the moment, you'll notice that at B and at D, which are the locations of the supports, if the unit load is above those supports, all the load goes directly into the support, which means that there's no effect on the moment at point E. So in a companion video, I'm going to go through the same example, except using the Mueller-Breslau principle in order to draw qualitative influence lines and show how we can skip some steps here where we don't have to calculate all of the reaction influence diagrams.